Like all the higher animals, we need to be aware of what's happening around us. Information from outside our own bodies gets to our brains through our senses. At the moment, you're using your sense of hearing. This is very important to human beings because a lot of our communication with each other is made through speech. But we also depend a lot upon our sense of vision. In this program, we'll have a look at the way in which we see and hear. We'll start with the sense of vision, how we see. This means investigating the human eye. Here's the eye in cross-section so that we can see inside it. It's fairly complicated, so we'll take things one step at a time. There's the outline of the eyeball. Now, in many ways, the eye is rather like a camera. There are three things about a camera like this which the eye has as well. First, a camera needs a lens which collects the light from the object you're photographing and focuses it on the film behind. In the eye, light is collected and focused partly by the cornea, the bulge at the front on the left, and also by a lens inside the eyeball. You can see the lens in this cross-section of an actual eye. Here's the lens seen from inside the eye. It's that grey disc in the centre. Now, the camera lens is focused by moving it in and out according to your distance from the subject you're photographing. It's actually done by twisting the lens on its mounting, which pushes the lens in or out according to which way you turn it. The lens in the eye is held by muscles. The lens is flexible, and when the muscles holding it contract or relax, they make the lens thinner or thicker, so that it can bring into focus objects at different distances. A different mechanism from the camera lens, but the purpose is the same. The lens of the camera brings light to focus on some photographic film. You don't get a picture immediately, of course. The film has to be taken out of the camera and developed first, but it's the film which reacts to the light falling on it through the lens. The eye, too, has to have a light-sensitive surface which will react to light falling on it. It's called the retina. Light falling on the retina doesn't produce a picture on it. What it does is to cause electrical impulses to pass out from the back of the eye along the optic nerve to the brain. This is quite different from the way in which film works in a camera. But there is one important resemblance. You have to control how much light falls onto the film. The camera lens has what's called an iris diaphragm, which can be opened or closed so as to let more or less light through onto the film. This is simply a way of making sure that exactly the right amount of light hits the film to produce a good picture. This is how you set the diaphragm to the aperture you need. The smaller the aperture, the less light can pass through the lens. This is a very small aperture. And it's not right for this picture of Jackie. She comes out looking too dark. Not enough light from her has got onto the film. If we set it for a very large aperture, then a lot of light can get through the lens onto the film. What happens if we take a picture of Jackie with the lens like this? Too much light, the picture's thin and the colours are wrong. For any subject, there will be a correct setting of the iris diaphragm. For that portrait of Jackie, if we try it set like this so that not too much and not too little light can pass through the lens, we get a picture that's not too dark or too light, but just right. Similarly, the eye has a way of making sure that the right amount of light falls on the retina. This is very important. If we're looking at something in dim light, the eye needs to let in as much of the light as possible. But if there's a very bright light, it might damage the delicate retina, so some of it must be kept out. Watch what happens when this spotlight is shone on one of Maggie's eyes. The dark centre, the pupil, gets smaller as her iris closes in, just like the iris diaphragm of the camera lens. The light's turned down and her pupil dilates, gets bigger, as her iris opens up to let more of the light in. Bright light, the pupil contracts to keep out some of the light. Dim the light, it dilates to let more of it through. Watch that again. Here's a diagram. The iris works like a shutter, opening and closing over the front of the lens according to how much light is falling on it. The eye then focuses light onto the retina, making sure that the right amount of light gets through. If our vision's normal, we can recognize the shape of things we're looking at, we can follow their movement, and we can also pick out different colors. How does the retina work? What happens when light falls on it? Here's a very simplified picture. There are special detectors in the retina. Some of them are called rods, and they look a bit like this. The rods cause electrical impulses to be sent to the brain when light falls on the retina. The rods around the edge of the retina are especially sensitive to the movement of light. That's why we so easily notice movement out of the corner of our eye, on the outside of our field of view. Let's do an experiment. Turn your heads away from the screen and keep your eyes looking straight ahead at the wall or something so that you can only just see the screen right out of the corner of your eye. As soon as we make it flicker, you'll notice the flicker out of the corner of your eye, even if your eyes are turned away from the screen. The flicker is affecting the rods around the outside of your retina. But if you're doing it properly, there's one thing you won't pick out so easily out of the corner of your eye, and that's any colour on the screen. Even when the flickering light changes colour, it's difficult to spot what colour it is if you're only seeing it on the very outside of your eye's field of view. Now look at the screen again. When we look straight at something, we easily recognise its colour. We're then using the most sensitive area of the retina in the centre. Here, as well as rods, there are structures called cones, which look a bit like this. There are 125 million rods and 7 million cones in the retina as a whole. And most of the cones are in this sensitive central area. The rods here tell us how bright the light is. The cones detect certain colours. Some of them react to light that's magenta-coloured, a kind of red, the one in the middle. Others react to a greeny-blue colour, like that one at the bottom. Yet others are sensitive to a yellow colour, like the one at the top. But suppose we're looking at something that isn't red or green or yellow. Well, any colour is a mixture of 2 or 3 of those colours. Brown, for example, can be made up from red and green mixed together. So when we see something brown, this colour triggers off the cones sensitive to red light and those sensitive to green light. And the brain receives the nerve impulses from these cones and says, ah, red and green, must be brown. And so with any colour. There are lots of things still to be found out about how the eye works. That was just a simple picture. Now, what about another important sense, that of hearing? Sounds are caused by waves of compressed air coming from whatever's making the sound and passing through what we call the ear to the real organ of hearing inside our head. These sound waves travel along this passage until they reach the eardrum. This really is a sort of drum skin which gets hammered so that it vibrates. The skin of a real drum is hammered and made to vibrate by the drumsticks. The eardrum gets hammered by the waves of air pressure which hit it when we hear something. This makes it vibrate considerably, and these vibrations are picked up by a little bone on the other side in what's called the middle ear. Next, the vibrations pass along a little chain of tiny bones called the ossicles, and as they pass from one bone to another, the vibrations get less violent, so that they won't do any damage when they get to the inner ear, the really sensitive part. This is called a cochlea, looking like a snail shell. Cochlea is Latin for snail. This part here has nothing to do with hearing. It's concerned with keeping our balance. It's the cochlea that gives us our sense of sound. That was a model. Here's a real eardrum fixed in part of the skull. You can see how delicate it looks, and you can see the bone attached to it which passes its vibrations to the ossicles, which are very tiny. Here's a set of real ossicles sealed into a piece of transparent plastic. The whole mechanism of the ear is very sensitive, which is why loud noises can easily damage it and make us deaf or partly deaf. Another model of the cochlea. The tiny vibrations from the ossicles pass into this hollow spiral which contains a liquid. The vibrations, caused by whatever we're listening to, pass along the liquid in the spiral. Let's look inside. The vibrations in the liquid are picked up by tiny hairs attached to a membrane. It's believed that high-pitched sounds are detected at the start of the spiral, then the hairs pick up lower and lower notes as we spiral up to the centre. The hairs which pick up the vibrations are connected to nerve fibres which send electrical pulses to the brain. Let's look behind the cochlea. There's the nerve. The brain has the job of sorting out the different signals coming along this nerve from different parts of the cochlea and of working out what they mean. In other words, making us conscious of exactly what we're listening to. The complicated mechanism of the ear is there simply to turn sound waves into electrical impulses which the brain, our built-in computer, can sort out and interpret for us. At the same time, it does the same for the electrical impulses coming along the optic nerves from the retinas of our two eyes. It's our brain which enables us to make use of all our senses, touch, smell and taste, as well as seeing and hearing, and to make intelligent use of what they tell us about the world we live in.